Thanks, Karen, for that. I like your confidence in me that I'm going to really explain the moment maps because this is not my area. So Karen is our spectral lines guru. So if you have any questions about radio spectral lines, definitely ask Karen and not me. I'm a transient astronomer. So if you're interested in more info about FRBs, anything that flashes, a little bit about pulsars, and I also work on radio stars. And like Karen is a project scientist of the Wallaby survey with ASCAP, I'm the project scientist of the VAST survey with ASCAP, which is the variables and slow transients survey. So I cover radio stars and variables and transients. So happy to chat about those things. But compared to Karen, who does spectral lines, I do what we call continuum in the radio, which I like to think of as not spectral lines. I'm sure there's a better definition of it, but I don't look in at such high resolution frequency observations. We still get a lot of really good frequency resolution, as I'll get into, but not looking into those details. So just like Karen had a tricky task fitting all of that in, I have a tricky task fitting all of this in. So I'm going to talk about radio observing in general, but I'm really going to focus on radio facilities in Australia. But I am hoping that this kind of whirlwind tour will also help you think about other facilities that you might use across the world, because I do think that Australia has a little, radio astronomy has a little bit of a PR problem. It's hard to get other types of astronomers to do radio observations. But hopefully with what I share today, you'll see that there's a lot of data that you could already access now that's science ready, and you don't even need to do anything except download the data. So I'll start with talking about facilities, and that's going to be the main part of my talk. So I'm going to try and keep it really practical, and I won't focus too much on the science because Karen just gave us a really nice overview. So let's start by talking about different types of telescope. I was going to talk about different observations, different science, but I figured it's the best place to start is different types of radio telescope. And of course, many of you will be familiar with these, but just in case you're not, one of the main types of radio telescope that we have, I suppose, kind of the traditional type of radio telescope, and what most people, if they even have heard of radio astronomy before, would think of when they think of a radio telescope, is a single dish. This, of course, is the Murray-Yang or Parkes radio telescope here in New South Wales, and it's 64 meters in diameter. But a single dish, I like to think of it as like having a single pixel on the sky. And because we only talking about a single pixel, or in some cases, maybe a couple of pixels, but still single pixels, no resolution, imaging is not great. What you're talking about is, look over there, how bright is it in that one spot? But the advantage of this is it's much computationally much cheaper than doing imaging. But of course, we're greedy, so we don't just go, oh, okay, cool, it'll be cheaper for us computationally. We instead think, how can we make it computationally more expensive? And we do that by either increasing the band of the frequency observations that we can do, so a much wider band, higher frequency resolution, and also higher time resolution. So because it's computationally cheaper, that means we increase the computational expense by increasing the frequency resolution and capability and the time resolution as well. So radio definitely has, single dish definitely has its advantages. The other thing that we do, of course, is interferometry, because if you try and keep building dishes bigger and bigger to get better sensitivity and better resolution, eventually gravity just says no and your whole dish collapses, which is not ideal. And also big dishes take up a lot of space. FAST in China is currently the biggest dish, and it's 500 meters in diameter. So that takes up quite a large area. So what we do instead is we take a whole bunch of mini telescopes, spread them out, and then add up the signal to simulate a much bigger telescope. This is ASCAP, which I'll talk more about later, and it's spread out over 6 kilometers. And so that is effectively simulating a telescope that's 6 kilometers in diameter. This is much more computationally expensive, but we get to have images instead, and we can almost do a really similar thing to single dishes too. But one of the things that's important to remember for interferometers is that we actually lose that really large scale structure. So what we call the zero baseline, which is what's provided by single dishes. So if you want to see the really big stuff, you do need a single dish. If you want resolution and to make an image, then you need to use an interferometer. But of course, our interferometers don't need to be dishes. Radio astronomy telescopes can look really weird. I like the MWA, which is this telescope. it looks like spiders spread out across the beautiful Australian outback. And it's a bit different, but we have telescopes. Of course, the SKA is going to look like Christmas trees instead. So really all you need is a wire and you can detect radio light. So we tend to take advantage of that. These are, of course, a lot cheaper to build, and you can build a lot more of them, much more easily replaceable, as long as you don't put them out too remote. But of course, we always put them remote to avoid RFI, radio frequency interference. And so these have a lot of advantages in that you can point them wherever you want digitally. Instead of needing to actually point a dish, you can just point it kind of later, record the data and point it later. And you can also just use these to do imaging and also time domain data, which I'll talk about more later. But antennas have a lot of advantages. Computationally, again, really tricky, because now we're not talking a couple of tens or a handful of dishes. We're talking about hundreds to thousands of antennas. So that increases the computational challenges. And for a bonus, interferometry, you can do very long baseline interferometry, which is where typically you take different telescopes across the country, across the world, across the continent, and use all of those telescopes together as one giant interferometer, and you get very, very, very high resolution observations, milliarc seconds, sometimes even better than that, nanoarc seconds. And so really, really excellent resolution. But of course, using different telescopes that have all their different specs is an extra challenge. It's computationally challenging, and it's just technically a really difficult thing to do. But if you want to see things moving, if you want to resolve jets, absolutely fantastic. So VLBI, also an option if you like to do radio astronomy on hard mode. So those are the different types of telescopes, particularly the different types of telescopes that we have access to here in Australia. There are lots of different types of observation as well that you can do with these different telescopes. And you can often do a lot of these with either a single dish or an interferometer. So I also want to note for the radio astronomers who are here, of course, there's a lot more things that you can do if you're a black belt, but these are some of the things that you can do without having to find a radio astronomer. So this isn't how we usually start with radio astronomy, but this is perhaps one of the most familiar things that astronomers do, particularly optical and X-ray astronomers. So I sort of thought I'd start with imaging. This is an ASCAP image. So in radio, of course, we can make images. It isn't like taking a photo. There's a lot of steps and a lot of computing. It often takes hours to go from data to image, but we can make images. And the advantage of imaging in radio astronomy is that we can do an 8-hour-long observation. And then depending on the minimum integration time available for the telescope, you can actually slice that up afterwards. So I think we don't talk about this enough in radio, but most other types of astronomy can't do this observationally. So ASCAP, for example, the minimum integration time is 10 seconds. So we could do an 8-hour observation and then later on decide to chop that up into 10-second pieces. And it's the same with frequency. ASCAP has a frequency resolution typically for continuum observations of a megahertz, smaller if you do spectral lines like Karen does, but then much bigger data sets. So we can do the imaging and then later on we could divide that up into 1 megahertz images. So really great for time domain, looking at frequency spectra, which Natasha will talk about later. So it's difficult to make images, but there's a lot of recipes and cookbooks out there for different telescopes. ATCA, for example, has a great sort of cookbook that you can follow, but lots of advantages. Shamelessly stolen from Karen, and I won't go into details because Karen already did. We can do spectral lines. For radio astronomy, you don't really need a different telescope. You just need to set the observing modes that you're getting that extra resolution in frequency. So it does increase the data rate, but then you get to see all this fabulous H1, which, as Karen showed, is kind of radio astronomers' favorite line at 1.4 gigahertz or 21 centimeters. So for most telescopes can do this sort of thing if you're ready for a lot more data to get the higher resolution frequency information. And like Karen showed us, this means that you can get a whole lot of extra information. She talked a lot more about it, and definitely ask her and not me, but you can get these moment maps, including the velocities that Karen showed. So we can do imaging, we can do spectral lines, and we can do basically spectral imaging as well. So you can either look at it like a spectrum, or you can look at the imaging so that you can get the velocities and things like that. We can also do something called intensity mapping. This is typically done with those single dishes. I couldn't find a good radio comparison between a high resolution image and a intensity map, but it's the same thing. This is an optical example. So this means you're basically taking out all the details by using one of these single dishes. So instead of trying to make images where you're getting every single little detail, you are just going across the whole sky and saying how in this, you know, arc minute size beam, even bigger, how bright is it? So you're kind of getting a smoothed map of the sky instead, really seeing that beautiful big structure. Really handy for cosmology. But also in this example, this is an H1 map done by Parkes. So just using that one giant pixel across the sky. And you can really see this beautiful large scale structure of the Milky Way. And don't quote me on this, but maybe in Magellanic Clouds. I don't know, not my area. But you get really a different large scale picture of the universe and the Milky Way when you do this intensity mapping as opposed to making images. And last but certainly not least, time domain. Karen already showed us some dynamic spectra. So this is frequency and time and brightness or flux density. This is an FRB that has the dispersion measure has already been corrected, so it's nice and straight. This is really, we do this with both single dishes and interferometry. Lots of advantages to both of those. Interferometry, you can actually, those single pixels that you have with a telescope like Parkes, you can reconstruct those and have a whole bunch of them. For example, with Meerkat, we can do 700 coherent beams across the sky and do those same time domain searches, but with a bunch of pixels instead of one pixel. But we can also make these dynamic spectra using imaging data. So we can do it on longer time scales, like the 10-second time scales with ASCAP. So we do that too. And of course, like any classical astronomy, we can just take multiple images of the same patch of sky to see if anything changes. But then this comes back to how we can divide images up later. So we can do an 8-hour observation, divide it up into 1-hour parts and see if anything changes on those time scales. So time domain really encompasses a whole lot of different types of observations. And I nearly forgot to put this slide in, which would have been embarrassing because I do a lot of circular polarization stuff. But with radio observations, we pretty much get, I'm not going to say for free because there is still a lot of cost of processing, but radio telescopes naturally have polarization. So on the left here, we can see full polarization. So Stokes I, this is just everything. And on the right here, we've got Stokes V or circular polarization. And you get both of these with ASCAP. And you can see there's a whole lot of mess going on in the full polarization image. In particular, this wasn't very well cleaned or deconvolved in the imaging process. So there's a lot of mess going on here, lots of artifacts. But then as soon as we put sunglasses on the telescope, that removes a whole bunch of stuff. And this is really powerful for the work that I do because the only things that we see that are highly circularly polarized are galactic, particularly pulsars, stars, and mystery things. So it's really nice to be able to kind of put this filter on so that we're only seeing the things that we're interested in. But extragalactic things also have linear polarization, and we can get that. It does take a bit of extra processing, and usually it takes a telescope a couple of years to kind of really get the polarization nailed down. But once it is nailed down, it's a really powerful tool. And you just get this, if you take observations, you get the polarization information, so long as you asked for a polarization calibrator scan. So don't forget that. And we can do this in time domain too. So this is sort of cheating. These are ASCAP observations, but that's fine. So these are all dynamic spectra, but in different polarizations. So we've got full polarization. We combine Q and U to get linear polarization, and we also have circular polarization. So this is a really powerful tool. And we sort of do this in radio astronomy almost as a matter of course in a lot of different fields. So we do need to talk about frequencies. This is a little bit harder to define because it's a very hand wavy what the limits of what we'd call low frequency and mid frequency and high frequency, but radio astronomers do tend to use low frequency to mean up to a few hundred megahertz. Mid frequency is kind of around a gigahertz and a little bit higher. And then I put everything else for high frequency because I've had lots of discussions with people about how high is too high for it to be radio? Like, when does it become sub-millimeter? And I have yet to have anyone give me a really nice, clear answer on that one. So we just put that discussion to the side. As Karen showed, there is a window. The absolute minimum we can see from Earth is 10 megahertz, but typically it's actually a bit more than that because it has to be a really nice ionosphere-free night, typically night, because the sun causes issues as well, to be able to get down to 10 megahertz. But I think what's important here from the observing perspective is that radio telescopes kind of have a couple of different options. They might have specific bands, so you can observe between a specific range of frequency because of the receiver that they have. Or some telescopes will have a sort of a window, and then within that you can choose a smaller window yourself and slide that around, and that gives you your observing band. So they might be able to observe between 1 and 2 gigahertz, but you can only see 200 megahertz at a time, but you can slide that sort of wherever you want. It could be at 1.4 gigahertz central frequency, 1.8 gigahertz central frequency. So there's different options depending on the telescope, on whether you can choose a specific band and that's what you get, or you get to kind of have a little bit more flexibility within the observing range that that telescope can observe. But typically, unlike having a filter with a radio telescope, you get that band and then you can slice that up into smaller pieces inside that band. Different types of observing. So this is very practical information. So different telescopes do things different ways. It's for some telescopes, you have to sit at a computer, or sometimes you might have to visit the telescope and you're actually in charge of the telescope. From Australian telescopes, it used to be that you had to visit them, but now it's all online. So you can do it from home, but you have to set up the observations. You have to press go. You have to have the schedule ready to go, and you have to make sure that there isn't a lightning storm nearby, or it's not ridiculously windy and it's going to blow the telescope over. So you're actually in charge of the observations. And then once you've done the observations, they go, here's your data, enjoy, and you have to do all the processing. So sort of from scratch. Most of the time, it's not truly from scratch because that would be very inconvenient for everybody, but relatively from scratch, you don't get an image, you just get numbers, imaginary numbers, and then good luck. In other cases, the observatory does the actual observations. You don't have to control the telescope, but then afterwards, they just, again, they say, here's the data, good luck. And then other telescopes, the observatory does the observing and the processing. And then at the end, you get both science-ready data and the effectively raw data, because often the science processing that they do is a pipeline. And for those who are specialists or black belts in radio astronomy, they want to do the processing themselves. But if you're just doing something a little bit more standard, usually that data is perfectly science-ready and ready to go. So those are sort of your options. Typically, they wouldn't do the processing for you, but make you do the observations. So these are kind of the three options, particularly within Australia, that we have. So let's chat Australian telescopes within that kind of framework of the different telescope type, the different types of observations, the different observing strategies, and the different frequencies. So we'll start with the classic. For those of you who have ever seen the movie The Dish, you'll know this one. If you haven't seen The Dish, I highly recommend it. It's very Australian. But Parkes is a single dish. It doesn't just have one pixel, it has a multi-beam receiver, so it has multiple pixels, but still effectively single pixels. Parkes has quite a few advantages and kind of things that it can do. It has some really, really, really wide bandwidth receivers, which is a huge advantage, particularly if you're doing pulsar observations or spectral lines. And it has multiple receiver options. I couldn't include them all on here, but it has lots of options for the kinds of observing that you can do with it. It's really good at time domain, particularly things like pulsars and FRBs, but it can also do spectral lines, maser observations, and as I've showed a couple of slides already, really good at intensity mapping, and there's quite a few surveys on that. Parkes is an ATNF telescope, or Australian Telescope National Facility Telescope. You have to do the observing and processing, and the ATNF has 2 open calls per year in June and December if you would like to propose for observations. Of course, CSIRO doesn't just go good luck. There is there is an observing guide, but they also can provide assistance. You still need to do the observing, but they'll help train and help you observe. The Australia Telescope Compact Array, or the Compact Array, or ATCA, is an interferometer, and it's a bunch of 22-meter dishes. It's currently undergoing an upgrade to the back end, so the receiver, which kind of changes what bands it observes in and the band width. So it's going to have a really wide frequency band, which is going to be amazing. I'm super excited to see the spectral structure of things. But traditionally, it's had 5 bands that range from 1 gigahertz to 100 gigahertz. So ATCA's big advantage is that it's really flexible when it comes to observing. So it's fantastic at imaging and spectral lines because it covers this huge range. You can only observe a small part at a time, but it has a really big range, and it can also do sort of what we call zoom bands, which are really good for spectral lines. It's especially good for it has a smaller field of view, so it's really good for follow-up and targeted observation. And just like Parkes, it's a ATNF telescope, so you do the observing and processing, and there's 2 open calls per year at the same time as the Parkes open calls. My personal favorite at the moment, because it's the telescope that I use all the time, is ASCAP, and it is 36 dishes spread out at the beautiful observatory site. And ASCAP's huge advantage is its enormous field of view in radio astronomy terms for L-band. MWA actually has a bigger field of view, but for L-band observations, this is a very big field of view of 30 square degrees. So it's a survey instrument. It's really good at imaging. It also does spectral lines, as Karen talked about, as the project scientist of Wallaby, and really, really good for time domain, which I do the imaging and time domain side of things. It has a relatively, still very wide, but relatively small compared to some other telescopes, wide band, but you can shift it sort of anywhere you like between 700 and 1700 megahertz. This one, the observatory does everything. It does the observing and the processing and makes the science-ready data available publicly. It mostly does surveys, but it does have 2 open calls per year. Then we have the fabulous MWA, which is Natasha's main telescope. So if you have any special questions about that, I'll pass them over to Natasha because she's the real pro. Though it was the first radio telescope that I used. I used practice VLA data, and then I used the MWA. So it has a place very close to my heart. It is 4,096 of these little spider antennas. Again, it's next door to ASCAP. It has a bandwidth of 30 megahertz, but again, you can kind of slide it at very low frequencies. So the MWA, one of its big advantages in Australia is that it is really low frequency, whereas a lot of the other telescopes, including ASCAP and ATCA and Parkes, all do cover L-band instead of really pushing to those low frequencies. So MWA is great for that. Because it's low frequency, it's a bit lower resolution, but a much larger field of view, up to 50 square degrees. And the things that I know it for, at least, it does a lot of things, imaging and time domain, really fantastic. I believe, and Natasha can correct me if I'm wrong, the observatory does the observing, but you do the processing. But I actually struggled to find that information. Maybe this is feedback from a fellow radio astronomer. It needs to be a little bit more publicly available. If you have a comment on that, maybe pop it in the chat as well. And the open calls, I had a bit of a look. It does shift around a little bit year to year, but there is sort of an earlier, I think it's open now. It's a bit earlier.
Just closed.
Just closed, damn it. But there's sort of an early part of the year and then a little bit later in the year. But keep an eye out because it did seem to shift around a little bit year to year. But definitely ask Natasha for more info about the MWA and the observing. Then we have the LBA. This is the VLBI in Australia. So if you want extra good resolution, really tiny field of view, really amazing resolution, a few options for observing frequencies. LBA and VLBI is really the black belt of radio astronomy. I wouldn't do this myself. I would definitely be asking the experts for help. So if you want to do this, it's fantastic and I highly recommend it, but it is trickier. So you do need kind of a radio astronomy partner who is an expert in this to help you out with proposals and then later with the observing and processing. This is ATNF as well. So there's 2 open calls per year. So I have a little summary for this. It's a little bit of a pause, but I'm going to go into surveys, and I know I only left a little bit of time for this, but the surveys section, I really just want to give you a really brief overview. There are way too many for me to ever come close to covering them, but hopefully I give you enough of a little bit of a taste that you can really see that there is probably a lot more radio data available than you ever thought. And part of the reason that you might not have realized it is because we're not particularly good at putting that data in places that people go, like Vizia. So we're working on it. I'm trying to convince everybody that they need to put the data somewhere that people already look, but let's get into it. There's a whole bunch, so mentally prepare yourself. I will share these slides, and I put links in here so that you can see what's up. Don't worry when I know that I'm over time, but I'm gonna really whip through this. So just to note that the ASCAP surveys are all ASCAP data are publicly available at that link there. I'm happy to share later on in the evening/morning, talk a bit more about that and do a demo. There's a whole bunch of ASCAP survey science projects. And here is all the information you could ever need about them, but I'll leave you to look that up for yourself later. The integration time, I suppose the summary is that these observations do vary a lot depending on the survey project. They could be from 12-minute observations up to hours, 10 hours, 12 hours. They cover a range of frequencies, but they're all publicly available. RACs are the all-sky surveys by ASCAP. There's already been 5 all-sky surveys below plus 50 degrees DEC, and there's already one underway. They're 15-minute pointings. But what that means is that if your source is below plus 50 degrees declination, then it's already been observed by ASCAP at least 4 times, probably 5 times. Whether it's been detected or not is a different question, but observed, yes. MWA also has a couple of fantastic all-sky surveys, and Natasha really is the pro in these. You can see down here the difference between GLEAM, which is the original one, and GLEAM X, which is the second GLEAM survey. She's also monitoring the galactic plane for transients and has already got some really exciting things coming out of that. And scintillation is another thing that MWA really excels in. Parkes has a bunch of surveys, mostly legacy surveys and intensity maps. We've already talked about a couple of those. And of course, Parkes is really the boss telescope of pulsars. Have a look in the pulsar catalog if you love pulsars, but I'm sure if you love pulsars, you already know about the 18F pulsar catalog. And of course, there's a bunch of other surveys. ATCA isn't particularly an all-sky survey telescope, but it has done a few surveys of particular types of objects. So check those out. And there's a few other surveys in there. So it's too tricky to go through all of them in detail because there's just so many, but there's so much data available. And all of those surveys, the data are publicly available, and the ASCAP data is totally publicly available. LBA, so 18F data is proprietary for 18 months and then public, same for MWA. So there's a lot more data out there than you might think. And I will finish by just saying that, as I said, if your source is below plus 50 degrees DEC, it's been observed multiple times just by ASCAP, let alone by all of the other telescopes that we have in the Southern Hemisphere. Thank you.
Beautiful. Many thanks, Laura, for this comprehensive talk. Very interesting. I also learned a lot. So,
excellent.
Are there questions? Mara.
That is unfair.
No, it's good. You've always got to have the person who asks questions.
Yes,
so thank you, Mara. We appreciate it.
No, so
absolutely.
Actually, I was able to follow everything, and
Yes.
the question that I had really, how do I assess the data? You put it on the previous slide with the link, so it is clear to me. I was wondering whether there is some where the data are stored, whether there are tutorials that can be used for learning how to reduce the data, how to assess them, because I mean, it's nice to know that all this is publicly available. We are now in this school giving a bit of an overview, but I think still having an idea where the tutorials are, that will be important. I still underline that the idea is that we are collaborating. So if from eROSITA side we have an idea, we should contact the radio expert and do the work together. But still, people may want to be trying to reduce the data by themselves. So I was wondering whether there are tutorials available for the various things that you were presenting.
Yes, definitely. So Muriang and Atka have been around for many years. So they actually have some pretty excellent tutorials that go through what software you need and have a step-by-step of like how to make an image. The ASCAP data, it's science-ready data. So there's actually source catalogs. So they've done the source extraction already and FITS images that you can just download and open in DS9 and you have a radio image. And that is pretty revolutionary because it is tricky to reduce radio data. It is better to have a radio astronomy friend or collaborator because it is hard work. The LBA is a little bit trickier. It is just a little bit more of a specialist instrument. So for that one, I definitely recommend find a friend and phone that friend. But Muriang and Atka for sure. And Natasha, do you want to speak a little bit about what's available for the MWA?
Yeah, I would say the MWA is pretty challenging even for a black belt radio astronomer. There's a lot of considerations, but one thing I'll touch on my talk a lot is that a lot of the time we'll get a small group of radio astronomers together and do our best to produce a survey that you can then use.
Yes.
So yeah.
That is easier. So the ASCAP data, basically you can use them. It is helpful to have a bit of radio knowledge, but you can just sort of use it out of the box and you can do the black belt stuff if you really want to. And Muriang and Atka data are actually, in the scheme of radio, more straightforward to download and process because those recipes are available. Maybe before I share these slides, I'll update this one just to have the link to that information too. So it's definitely possible. And all of those surveys that I talked about, Gleam, especially for the low frequency stuff, because it is hard. I'm also scared of processing low frequency data, even though I've done it before. So yes, there's a bit of a